VLSos here. This is a video lesson on solving logarithmic equations. First, let's remind ourselves that the notation log base m of a equals n is a logarithmic equation in general terms, and that means what we're looking for is equivalent to thinking m to the n is equal to a. When we ask, what is the log base m of a, we're wondering what power of m will equal a. This is not a log property, it's an equivalence between a logarithmic form or equation and its inverse exponential form with its equation. They're inverses of each other. Before looking at some log properties and log equation examples, it's worth noting how often this notation is mistaken for each other. Log base 10 is an operation. Log base 10 is incomplete because it has nothing after it yet that we would take the log base 10 of. This notation means log of 10. And if we don't see the base written, it's because we're expressing this as common log whose base is 10. This log of 10 is a number. We can evaluate it. It's enough information in order to turn it into a number. Numbers are like nouns. They're objects, things. Similarly, if we had 4 divided by 2, we would be able to do the math and simplify this to a number. This notation, log base 10, it can't be evaluated, it's incomplete. It would be like saying divide by 2, and then it begs the question, what are we going to divide by 2? Dividing by 2 is a verb. It's something that we do, it's an action that we take. In math terms, we call it an operation. We wouldn't confuse the difference between divide by 2, which is something that we're going to do to numbers, and 4 divided by 2, which is complete math that can be done and turned into a value. But very often when we see these two representations, we get confused. So make a note, log base 10, or log of any base, is something that you're going to do to numbers or variables. It's an operation. Where log of 10 is a number in itself. It can be calculated. Log properties can be very useful. Very quickly, I'm going to list log properties that are worth committing to memory. Log base m of the product a times b can be converted into log base m of a plus log base m of b. We call this the sum of logs property. Because if we have the sum of two logs whose base are the same, we can express it as one log with the product of their arguments. An argument is that what you're taking the log of. In this case, the arguments of these two logs are a and b. And the new argument can be converted into one log a times b. Here's a similar property. Log base m, whose argument is a quotient, a divided by b, can be separated into the log with the same base m of the numerator a minus log base m of the denominator b. Difference of logs property, if we're taking the difference of two logs that have the same base, then we can write it as one log of the quotient of their arguments. And we can use this vice versa. We can start with the log of a quotient and then separate it into two logs. Whatever is useful in the problem. Here's another log property, extremely useful. Log base m of the power a to the n. I can take the exponent in the n and then move it out front to make it into the equivalent n times log base m of a. This is a log of a power property. Very simple properties show the inverse between log and exponent. if I'm taking the log base m of the power base m to anything, then the log base m and the power base m will cancel out, leaving a. And it's the very same property, but seen a little different. If we have a power base n to a log base n of anything, then the power base and the log base will cancel out, leaving that anything. So with all of that, let's solve a couple of example log equations. Log base 2 of x is equal to 3 log base 2 of 4 plus log base 2 of 5. Careful, we have a sum of two logs, and the logs have the same base. But this side here doesn't exactly match the pattern because we're multiplying by 3. In the pattern, there's nothing that we're multiplying by here, so we can't use this property yet. I can think of this log term, 3 times the log base 2 of 4, as a log of a power, moving the 3 that's out in front into the power position. I can rewrite 3 log base 2 of 4 as log base 2 of 4 to the third. Just use the power property of logs. And I still have the log base 2 of 5, and on the right, log base 2 of x. Now the sum of these two logs is ready to use this property. I can combine the arguments a and b, in this case 4 to the third and 5, and write them with a single log as the product 4 to the third times 5. And on the left, it's unchanged. I can see in my equation that on both sides I'm taking the log base 2. I can take the power base 2 of both sides, and when I do, they will cancel out with their inverse, log base 2, leaving x on the left and 4 to the third times 5, which we may be ready to evaluate. 4 to the third is 64. 64 times 5 is 320. One more example. 1/3 times the log of 3x plus 1 is equal to 2. In this problem, I'm going to undo one operation at a time to get x by itself. I don't need a log property in order to get rid of multiplying by 1/3. I can divide by 1/3 or multiply by 3. And when I do, I get the log of 3x plus 1 is equal to 2 times 3 is 6. Undoing this log, I want to consider what its base is. If it's not shown, it's common log base 10. So if I power base 10 both sides, I'll clear that common log, leaving 3x plus 1. And on the right side of the equation, 10 to the 6th is 10 times itself 6 times, which will give me 1,000,000. Now what I need to do is subtract 1 from both sides and then divide by 3. Subtracting 1 will give me 999,999, and that can be divided by 3 into 333,333. Log properties are very useful.